Yeah, I started it and I forgot about it over the weekend, so I got that part, and then I filled them all out, just those boxes empty. So I don't know, like
how much would you give yourself out of 10?
It's so out of 10. I'd say a solid 7 because I did a good portion.
Yeah,
Would you say
so?
So I don't know which part you're checking, but I didn't do these sections.
Got 7.
Well, that was for the polarity stuff. So do you have? Yeah, I was looking more so for this stuff. 13 and 14. Okay. All right, let's take a couple minutes, real quick, discuss how many carbon atoms there are, how many H's are there, how many lone pairs of electrons, and how many double bonds. I think this is slide 26.
Slide 27.
Oh, 27, okay. I'm always changing my packets every year. So all the page numbers change pretty much every year, slightly off by maybe 1 or 2 pages. You gotta make it better every year. That way when kids fail and take it the second time, they get an even better chemistry class. All right, quick show of fingers. How many carbon atoms did you find?
I do.
Quick show of fingers. Carbon atoms. All right, I see a fair number of 3s out there. It's at the end of every line that isn't labeled, and it's at the intersection of every line that's not labeled. Good, I see 3 up here. See 3. All right, quick conversation. How many H's do there need to be?
2.
Well, no, this is where you discuss it with your small group members. Well, those are the only 2 that are drawn, but there's other H's up there. Carbon needs how many bonds? Carbon needs 4 bonds.
I got it.
How many hydrogens on this carbon atom? 1, good. How many hydrogens on this carbon atom?
3.
It's got 1 bond, so it needs 3 more bonds. You can either draw all the lines to the H's, or you can just abbreviate it CH3. This one has 4 bonds. How many more H's does it need?
None.
0. You add up all the H's, you get 1, 2, 3, 4, 5, 6. And then everything else is alphabetical after C's and H's. How many O's? 1, 2, 3. All right, double check. Look up the chemical formula for lactic acid. Google's really good at giving you answers for these.
Oh, yes, it is.
Did we get C3H6O3? I love it when we get these right. Now, quick conversation in your small group. How many lone pairs of electrons up here? Every atom should have an octet other than, let's say, maybe H and maybe B. So if it doesn't have an octet, rather than putting H's on those atoms, you need some lone pairs. How many lone pairs does this oxygen need to get to the octet?
2 pairs.
2. Good. Yeah, 2 pairs. Pretty much every time oxygen has 2 bonds, it's going to need 2 lone pairs. So if you were answering the question off to the side here, how many total lone pairs of electrons are there? 1, 2, 3, 4, 5, 6 lone pairs. Good. And then finally, how many double bonds are up there? Yeah, just 1, right? There's a double bond right here. 2 lines. So there's some really cool chemistry happening up here. Anytime you see an OH group, that would be an alcohol group. So if you take Miss G's organic chemistry class, you'll learn about functional groups. Functional groups determine the polarity of the molecule. We'll get to intermolecular forces probably tomorrow before the test. And then over here, anytime you see a COOH group, one of the O's is double bonded. This kind of looks like an alcohol, just like this over here. But anytime you have an alcohol attached to a C double bonded O, that turns it into a carboxylic acid. This H cannot really pop off, so that is not an acidic H. Whereas this H can totally pop off, and that gives it an acidic property, so that's why it's called a carboxylic acid. So COOH is an acid, OH would just be an alcohol. All right, quick show of thumbs. Double thumbs up, you'd be ready to take the test on this concept right now. Thumbs in the middle, after some extra practice, you'll be good to go. Thumbs down, you really don't see atoms. Doesn't really make sense why Mr. B's license plate says what it does.
What does it say?
It says I see atoms.
Is your kid named Adam?
What?
Is your son named Adam?
I was thinking about that, but my wife was like, no, I gave you Zinc for the dog's name, so you're not taking Adam for
Are you serious?
Yeah.
Your dog is Zink.
Yeah, and it was a lab. It was a yellow lab. Every chemist needs a lab.
I'm gonna be my chocolate chemist. I have a chocolate lab.
Say, like, there's ever a question on the test that said H had popped off with a carbon would go there, and that's supposed to say
Say that one more time.
like if H like popped off like carbon on this place since there's still a line, but it's just be nothing.
What do you mean an H pops off?
Like if you took an H off the
Like this right here?
Yeah.
I mean, you could do some really cool organic chemistry reactions, carboxylic acids. If you put like a carbon group over here, well, now this becomes an ester. So like if you've ever smelled, I don't know, candy and it's got like a special scent to it, those are probably esters. And I can make those chemicals in the lab. I can make a chemical, an ester. So if I just put a certain number of carbon atoms here, if I change how many carbon atoms are over here, I can make banana smells in the lab. I can make orange smells in the lab. I can make something that smells like a pear in the lab. There's so many cool organic chemistry reactions you can do. That's way beyond the scope of this class, though. I'm just going to say, here's a picture. You tell me what's not been drawn. Answer all the questions about that picture. Does that make sense?
Yeah.
But yeah, if you like where you're going with that, take Miss G's organic chemistry class sometime in the next 2 years, and you'll do all that cool organic chemistry. Now, if you would like some extra practice, I'd highly recommend writing down this website right here. So compound, I always got to look it up. Compound chemistry. Okay, yeah, so the website is called Compound Interest, but that kind of sounds like it's a math or a financial term. So the website is actually compoundchem.com. Compoundchem.com. And this guy has done all sorts of really cool infographics explaining the chemistry of all sorts of stuff. So here's a chemistry of plant flowering. What you really want to do is go up to this section that says infographic index. And you can pick topics, whatever topic you want. I would kind of steer clear of this alcohol chemistry. That's more for like, I don't know, adults and maybe senior college chemistry students. But yeah, we're not going to deal with that one. But I think some of the coolest chemistry is the ones that smell, kind of like those esters I was talking about. So you can pick any topic you want. And then, for example, if you want to know why cats smell the way they do, you take a look at this infographic here. Hey, wait a second, that's a structural formula. So you could figure out how many C's are there, how many H's are there. And then the cool thing is, if you type into Google, what is the chemical formula for felinine, it'll give you the correct C's and H's and O's and N's and S's. And if you got the same answer as that, that would count as like an extra practice problem. If you'd want to know cat ketone, there's actually a chemistry compound called cat ketone. You could calculate how many C's and H's and whatnot are in there. And then you type that into Google, what is the chemical formula for cat ketone? And if you got the same answer, you're probably going to get it right on the test. So there's all sorts of really cool things here. There's air fresheners. Look at that beast of a molecule. Mother's Day is coming up here. So lavender, why does lavender smell the way it does? You've got all these cool chemicals here. And again, each one of these you could type into Google, get the correct chemical formula, and see, did you see all the C's and H's correctly? Here's the smelly chemistry of the Titan Arum corpse flower. It smells like death, like literally. So you could take a look at that. The smell of garbage. There's some cool chemistry going on in the garbage truck. And it just goes on and on and on. The chemistry of why old books smell the way they do. The smell of wet dogs. So you could pick, and that's where I got my my example, the smell of rain. I took some of the pictures from one of his graphic organizers. So you could do as many practice problems as you want. Any questions on that? All right, so with that being said, let's take a look at our homework. Before we move on to polarity, we got to make sure that we understand VSEPR structure and the three-dimensional shape of molecules. So I think you had access to this answer key on Moodle, just in case you needed it. But let's go ahead and take a look at these VSEPR models. To get it big enough, again, we'll probably only be able to do maybe 2 at a time here, but that's okay. Now, I did have some students ask me, what's the difference between the domain shape and the molecular shape? So the domain shape is just kind of a stepping stone to get you to the right answer. Would you agree there's 5 basic shapes, 5 domain shapes? If one thing is attached, it's linear. If 2 things are attached, that's also linear, so we won't count it again. If 3 things are attached, get them as far apart as possible. The balloon models, that would be trigonal planar. If 4 things are attached, what's that shape? 109.5, the tetrahedral, yep. And then if 5 things are attached, it forms a pyramid going up and a pyramid going down with a triangle equator. Trigonal bipyramidal, yep. And then if 6 things are attached, square pyramid going up, square pyramid going down, it has 8 total faces, octahedral. So those are the 5 basic shapes. So if all of these domains would be atoms or X's, you're going to get the same exact shape. You only get a slightly different shape when you start covering up those X's and replacing them with E's. That's how we went from the 5 basic shapes to the 6 molecular shapes. Now, take a look at this over here. Would you agree this does not look like a tetrahedral? So then you want to redraw it so it does look like a tetrahedral. You can kind of make it look like that camera tripod. You can have that wedge coming out of the board, that dash going back into the board. You can add that like little perspective dashes there to kind of see the triangle at the bottom. But yeah, that looks like a tetrahedral. Eventually, you might start drawing these original pictures. If you think maybe a couple steps ahead, how do I get 3 things as far apart as possible? This would not be the best shape. So if you can start by drawing it more like this, in that triangle planar shape, maybe you wouldn't have to redraw the picture. Again, if you have all X's, the molecular shape is going to be the same as the domain shape. So for every one of these that you get right, go ahead and give yourself a point, and we'll see how we did out of 10. Any questions up through 2? All right, here's 3 and 4. Again, I technically did not need to redraw this one because if I already draw them as far apart as possible and linear, well, then we don't need to redraw it. This is very similar to the water molecule. These little Lewis dots are going, or these lone pairs are going to bend those angles away. So this is the first one where we're going to get a different shape. So the key thing is I have 2 X's and 2 E's attached. That's still 4 things. So then the question is, how do you get those 4 things as far apart as possible? So it would be about 109.5, probably going to be a little bit less. But then if you draw that tetrahedral shape, something that looks like this. Now, because 2 of those are E's, they affect the shape of the molecule, but they're not actually going to be included in the molecule. So then you just erase them. What's left? Something that looks straight? No, something that looks bent. So we're going to name it the bent shape, and it's just going to be a little bit less than the perfect 109.5. Questions on that one? Anybody else suffering from allergies right now? Fine, allergy season. Gotta love it. All right, then if you take a look at number 5. So we have 1, 2, 3, 4 things attached to the central atom. So we're still going to get that basic tetrahedral shape. But now I have to get rid of one of those domains and replace that with an electron pair. I think it's easiest to see if I get rid of this one. Would you agree that looks like a triangle pyramid? So we're going to call it a triangle pyramid. Trigonal, pyramidal. We just add some fancy endings to make it look like an adjective. Again, another example of an angle that's going to be less than the perfect 1 and 9.5. Since my original picture did not look like a triangle pyramid, you simply redraw the picture so it does look like a triangle pyramid. Anybody kind of like drawing these molecules? Kind of like the artsy side of chemistry. You get to draw pictures that go with things. Question?
So did the turn into a triangle because of the lone pair on the phosphorus?
You bet. So that lone pair is still here. The domain shape is still tetrahedral, but we don't count the electron pair as part of the molecular shape. So it's there affecting the shape, but we can't count that as part of. We can't say that this is a tetrahedral molecule. So when we cover that up, well, what's left is a triangle pyramid. Yep. All right, any questions up through 5? All right, here is 6 and 7. So number 6, we have 6 things attached, so that would be that octahedral shape. But now, because one of those things is an electron pair, it doesn't really matter which one of these we get rid of. I think it's easier to see if we get rid of this bottom one. And what is left would be something that goes up to a point. Oops. And it has a square bottom to it. So yeah, square pyramid. Square pyramidal. And the angle is going to be probably pretty close to the original 90s, but almost any time you have an electron pair, you could probably say that the angle is either close to 90 or maybe slightly less than 90. Again, for some people, drawing those extra little contour lines in helps you see that square pyramid. If you can get away without drawing those lines and you can still see things, then that would probably be best. And then number 7, you have all x's, so this molecular shape has to be one of your 5 basic shapes. So how do you get 5 things attached? Triangle bipyramidal, or trigonal bipyramidal. So you got a triangle around the equator, it goes up to an axial chlorine, and it goes down to an axial chlorine. Kind of like the Earth is spinning on its axis, kind of like a top spins on the axis. Questions up through 7? All right, here's 8 and 9. Number 8 is always a fun one to play with. The seesaw shape. So you started out with a triangle bipyramid. Something that looks like that. And now because one of those x's has been turned into an e, we got to get rid of one of those. Now the question is, do we want to get rid of one of the axial ones? And the thing with that is, if this is an electron pair, it's 90, 90, and 90 degrees apart from everything else. Whereas if we put that electron pair right here, that would make it 120 degrees apart from the other ones. 120 degrees is better than 90. So that would be the shape that you're left with. And if you turn your head sideways and go, whee, kind of looks like a seesaw. Unless you were cherry bombed as a kid. I mean, that's why a lot of playgrounds don't have seesaws nowadays, because kids got cherry bombed, they smash their fingers under it. When they got cherry bombed, they fall off, they break an ankle. It just wasn't worth the risk anymore. So we got the seesaw. The perfect angle would be 120 and 90. So the angles might be a little bit less than 120, a little bit less than 90. Number 9, very similar, except now we're going to get rid of a second one. And if you get rid of a second one in the 120 degree angle, you're left with the letter of the alphabet that kind of looks like a T. So Mr. T, I pity the fool. So pretty close to 90, pretty close to 180. Anybody watch the A-Team growing up? Yeah, it used to be a TV show in the 80s. Most people didn't remember, but then they came out with a remake movie with Mr. T and all the other gangs, so then people kind of got the joke. Thank goodness for remakes. I'm just waiting for MacGyver. All right, here we go. Number 10. So you got 6 things attached. They're all atoms. Octahedral stays octahedral. Everything's 90 degrees apart. All right, when you're done with that, give yourself a score out of 10. How many of those 10 did we get right? Sweet. Like it. Seems like this went fairly well. Are you getting to the point that you can kind of answer these maybe without looking at your graphic organizer? That would be the eventual goal, to work up to that. So as long as you know your 5 basic shapes and then can cover up things, then you just say, well, what does it look like? And if you kind of understand your basic geometric shapes, a lot of people can see these without having to memorize everything. If not, keep working at it. The nice thing is on the final exam, if you're having trouble with these, you could put that graphic organizer in your little index card, and then you'd be good to go. Any questions? All right, if not, let's go ahead and take a look at our polarity notes. The nice thing is the shape of a molecule helps us determine whether a molecule is polar or non-polar. Show of hands, you remember your bio teacher telling you that water is polar, right? I mean, that's really important to biology. Now, the question is, why is water polar? Because my bio teacher said so? Yep. All right. Well, in chemistry, we don't take our biology teacher's word for it. We're going to use our atoms to explain, well, why is water polar? There has to be something polar about the way the bonds are connected, and then overall, that kind of leads to molecular polarity. So we're going to look at both polarity from the bond perspective, individual atoms connected, and then we'll kind of take a step back and look at the overall molecule. So I believe this is on slide 29-ish. Somewhere around there. Flashbacks to the graphic organizer. Anybody take the time to cut theirs over the weekend? That way you got the little flat piece? Okay. I'd recommend doing that. And again, the beauty of that graphic organizer is you have all the examples. Just pick 3 random ones. Draw the Lewis dot structure. Take a guess at what the domain and then molecular shape would be, what the angles are, and then when you open up your flaps and find those examples, you can use that as your answer key to check whether you got them right. All right, here we go. Quick conversation in your small group. What is electronegativity? It's been about 2 units since we talked about that. What is electronegativity? I think 28-ish, maybe 29.
It's 28.
28, okay.
Electronegativity, negativity of an electron.
Not that far off. Electrons are negative. All right, back as a whole group. What is electronegativity? You can see up here, fluorine has the highest electronegativity out of all the elements, and it looks like cesium would be the least electronegative atom. We don't even worry about francium because, I mean, how much of that's even available on planet Earth? So the question is, what are we actually measuring if we're measuring electronegativity? Hayden says, well, it has something to do with electrons being negative. I totally agree with that. If you would be an atom like fluorine with a +7 core charge really close to electrons, are you going to pull them or are you going to push them away? You're going to really pull on those electrons. Would you agree electrons are shared in a bond? But there's nothing that says those 2 atoms have to share those electrons equally. An atom like fluorine is going to really pull on those electrons, and if you're pulling electrons closer to yourself, if you're kind of pulling negative influences closer to yourself, is that going to make you positive or negative? That's going to make you negative. If you're surrounding yourself with more negativity, that's going to make you maybe not totally negative, but some of that negativity is going to rub off on you. So that'll make you partially negative. That's what we mean by polarity. So we're going to look at the electronegativity difference to do this. So this is where it's really helpful if you have your periodic table out. All the electronegativity values are there. If there's a really big difference in electronegativity, we're not even sharing electrons. The one atom steals the electrons. If there's an in-between difference with electronegativity, we'll say that would be polar covalent, an unequal sharing of electrons. And if it's a really small difference, we'll kind of use 0.4 as the cutoff value. Then we'll say, well, that's such a small value, that would be a difference of 0. So without even doing any calculations, you know sodium chloride is what type of compound? Sodium chloride. It's ionic. It has to be. Metal on the left side, non-metal on the right side. Well, now let's use some numbers to support that. What's the electronegativity of chlorine?
3.
3.0?
Yes.
Good. What's the electronegativity of sodium?
0.9.
0.9. Now you'll notice why I set it up differently. I didn't take 0.9 minus 3 because that would give you a negative value. That's the difference between difference and subtraction. Subtraction, the order matters. Whereas difference, you just take the biggest number minus the smallest number. You want to know how far apart they are on the number line. So I took the biggest one. I knew chlorine was going to be bigger because that's on the right side of the periodic table. More positive core charge means more electronegativity. So I take the chlorine minus the sodium, and I get a difference of 2.1. And according to this chart, which maybe not every textbook would agree with the cutoff values, so that's the key thing here. Just keep in mind these cutoff values, there's no specific definition for this is ionic and this is covalent, or this is polar covalent, this is non-polar covalent. So it's a continuum, it's a spectrum, but you already know sodium chloride is going to be ionic, and this cutoff value, maybe I should make it wishy-washy, this is definitely a pretty big value. It's bigger than 2.0, so according to this chart, it would be ionic, which we already knew. Questions on that? All right, let's do H versus O. What's the electronegativity of O?
O is 3.5.
Good, and H is?
2.1.
2.1, a difference of 1.4. Is that enough to be considered ionic? Does oxygen steal the electrons? No. So they're going to share electrons, but it's not going to be an equal sharing. Oxygen is definitely an electron hog. Oxygen is going to pull those electrons closer to itself. So because that's between this value, we know it's covalent, but it would be considered a polar covalent bond. Oh, wait a second. Your bio teachers told you that water, which has H's and O's in it, is polar. Maybe this is the reason why. Well, it's partially the reason why. And then finally, CH. C would be what?
2.5.
2.5. H would be what? 2.1. Would you agree this is an unequal sharing of electrons?
No.
But because it's so small, again, I know this is a wishy-washy value here, but because this is such a small number, it's less than or equal to 0.4, we're basically going to say that this is an equal sharing of electrons. Technically, it's not, but it's so small, we're not going to really care about that difference. Questions on that? So would you agree, last unit we drew a little picture with a dot here. We're not even going to draw this as a line, but this dot goes over to here, making the chlorine negative and the sodium positive. Would you agree we did little Lewis dot structures like that? Whereas for something like H and O, we're not going to show the transfer of electrons, but we're going to draw something called a bond dipole. Oxygen pulls the electrons more. Why? Because 3.5 is bigger than 2.1. And that's going to make the H partially positive. So we're going to draw a dipole for a polar bond. You draw which way the electrons are being pulled, and then the other end of the dipole would be positive. If electrons are moving away from the hydrogen, that would make the hydrogen partially positive. So this is called a bond dipole. Not a dipole, but a dipole. It's a two-ended arrow. Sometimes people write that this is the partially negative end of the molecule, and this is the partially positive end of the molecule. That's just the Greek letter D for delta. It's not a full positive and negative like we have up here. but it's a partial negative and a partial positive. That's what polarity means. You have a two-ended molecule. Part of the molecule is negative, part of the molecule is positive. Why would we not draw a dipole for CH? They're sharing the electrons relatively equally, and because it would be a non-polar covalent bond, non-polar means no poles, no dipoles. So yeah, this is non-polar. Whereas this would be polar, and this isn't even covalent, this is ionic. Questions on that? So again, we're making this semi-quantitative by including numbers, but keep in mind there is no real strict cutoff value for what's polar versus what's non-polar. What's polar ion, what's extremely polar covalent versus what's ionic. But this will give you some kind of numbers to crunch to get a feel for, is it pretty ionic or is it pretty covalent? This is a nice picture representation of those dipoles. What's the difference between an F and an F?
F and an F.
Mm-hmm. There is no difference. So would you agree F and F will share those electrons equally? And that's what this Venn diagram is basically showing. This right here, if this is an F and this is an F, the electrons being shared in between are pretty equally shared. Whereas if we go all the way over here to lithium fluoride, what can you tell me about lithium fluoride without doing any number crunching? A what?
Looks like a light bulb.
Oh, kind of like a light bulb? Okay, but as far as the elements go, lithium and fluorine.
Those are one of the two most reactive elements.
Okay, lithium is on the left side, fluorine is on the right side. What type of compound is it? It's ionic. So they're not even really sharing those electrons. Fluorine is so much more pulling on those electrons, you can basically say that that lithium electron has been removed and goes over here to fluorine. So now lithium is a positive ion, fluorine is a negative ion. There's so little sharing taking place here. Lithium is extremely positive. So positive, it's actually a positive ion. And fluorine is so negative, it's actually a negative ion. Would you agree that's what we did last unit?
Yeah.
Fluorine steals the electron, leaving sodium being positive. Now, polar covalent is somewhere in between, right? It's kind of being pulled like this. It's kind of like ionic, but yet there's also a fair amount of sharing going on here. So in this case, this would represent the dipole. You can see the electrons are being pulled towards the F, not so much that it stole them, but it's really pulling on those electrons, making it partially negative, and then the H would be partially positive. That's exactly what that color rainbow scale is trying to show. So when you draw a dipole, that's really what you're drawing up there. You're showing that electron cloud kind of wobbling or moving to the one atom that's more electronegative.
Kind of looks like you're blowing up a balloon.
Exactly. But it's a lot easier to draw a dipole. An arrow showing the electron pool with the other end being positive than doing all the math calculations to figure out how big those balloons need to be. Now the computer MolView can definitely do all this. You can look up like polarity surface maps and it'll get you all of these pictures up here. But again, we don't need to go to that extreme as long as you understand the dipole. Questions on the dipole? Right here. So again, it's kind of similar to something we've already done. We did this last unit. It was that structure. Whereas now we're doing kind of something in between. It is a covalent bond, but it's an unequal covalent bond. The O is pulling the electrons more, making the H kind of positive. Not totally positive, it's not an ion, but it's partially positive. This is down here just in case if I wasn't here, you could read this. This is basically everything I just said. Any questions? So now the last thing is that those would be the dipoles in a bond. Would you agree if you have bonds that are polar, you would probably think the molecule would be polar? I would say that's a pretty good assumption. And if you have bonds that are nonpolar, would you agree you'd probably think that the molecule would be nonpolar? Right? No poles in the bonds, no poles in the molecules. That's a really good assumption. There is a third option. It's if all of the bond dipoles cancel. If they're pointing in equal and opposite directions, you could have polar bonds, but yet the molecule would end up being nonpolar. Let me just give you a picture representation of this. Tug of war. You have an atom pulling in the left direction, and you have an atom pulling in the right direction. As long as they're equal, the same atoms, but opposite, would you agree in tug of war the flag won't move, the handkerchief won't move? So in this case, the dipoles cancel. The bonds are polar, but their overall molecule would be nonpolar. Now that's kind of the tug of war picture. You could get really extreme. You could have like three-dimensional tug of war. The trigonal planar shape. As long as all three of those atoms are pulling in equal and opposite directions, we could prove it using some sines and cosines and tangents, all that sort of stuff. We could do it mathematically, but I'll let you save that for physics. When you talk about vectors in physics, you'll prove that these arrows cancel out. But for now, just take my word for it. It's kind of like your bio teacher saying water's polar. Okay, just take my word for it. The chemistry teacher will explain why it's polar. So again, I could teach you all the math to show you why those arrows cancel. Just at this point, take my word for it. In physics, you'll get to the math on why they cancel. Another one would be the tetrahedral shape. If all of these arrows are pointing in equal and opposite directions, in these three dimensions, all of these arrows will cancel out. So the bonds could be polar, but the overall molecule would be dipole. Or sorry, nonpolar. As far as the trigonal bipyramidal shape, one goes up, one goes down. They cancel. One goes this way, one goes back this way, and one comes out this way. Again, very symmetrical. All of those arrows would cancel. And then the octahedral shape. One goes up, one goes down, one goes back this way, one goes out this way, one goes back this way, one comes out this way. All of those arrows would end up canceling. So basically, if it's one of our 5 basic shapes, you can almost guarantee, as long as they're equal and opposite atoms being canceled, you'd have polar bonds but a nonpolar molecule. With that being said, any questions? All right, so at this point, I think you have everything you need to wrap up basically the second to last topic of this unit. So for homework tonight, you're going to do pages 15 and 16. The good thing is you already have the Lewis dot structures done for it. You might have already worked ahead and done the VSEPR pictures for it. So now all you have to do is look at the electronegativity difference. If it's polar, what do you have to add to your picture? What do you have to draw above the bond if it's a polar bond? A dipole. Which direction do you draw the arrow? Towards the more electronegative atom or the less electronegative atom? Thumbs up, more electronegative atom or less electronegative atom? Yeah, definitely be the more negative of the atoms, because then this atom would be less negative, which makes a positive. And then finally, if you see all the arrows moving in equal and opposite directions, even though you have polar bonds, you could write that the molecule would be nonpolar. So we'll check those 7 tomorrow, touch up any mistakes. And then the last topic of the unit would be intermolecular forces. There's 3 types. If you've been preparing for the vocab test, you might have worked ahead and you already know what those 3 types are. If not, we'll review that tomorrow. Review on Wednesday, test on Thursday. So notice how all week long you can come in for that optional vocab test, or if it's easier for you to do during Flex or Study Hall, the instructions are on Google Calendar. You just make that QuickTime video, 25 matching questions. Email me a copy of that video, and then I plug that score in for you. Quick show of hands, you're thinking of doing that vocab test this week? Awesome, sweet. Any questions I can answer? All right, rest of the time is yours to go ahead and get packed up. And again, pages 15 and 16 are homework for tomorrow.
No, it's not.